Right, so let's take a look what's this lab is about. So we're going to be basically investigating the application of the torque. That's the idea. So you know the center of mass, concept of center of mass. I think by now these concepts should be covered in your class, right? Center of mass means if you have a larger object, let's say I have object like that. So the mass distribute over the x-axis, right? Some length. Let's say this is a meter ruler. 0 to 100 centimeter distance. Now, if you can balance this object at one single point, you can balance this around like 50 centimeter location. So that balancing point is actually generally considered as a center of mass or center of gravity, right? So which means even though the object is larger, you can find a point, one single point, where it looked like total mass is actually acting on, force of gravity acting on. That point is actually called the center of mass point, right? So that's what we try to investigate, how to balance the object by with the different forces. Now, for example, if I want to balance the same meter ruler, let's say I have a meter ruler and then one end is attached right here. No, we'll say it's balancing exactly at the center of mass point, right? Let's say it balance here. So I have a pivot point here. It's balanced exactly on that point. If I draw a free body diagram now for this one, in this kind of situation, we would like to draw the free body diagram elongated along the object, okay? Not like the standard free body diagram, we like to draw exactly all the forces on the origin. But for this particular, the chapter, we would like to show the forces where exactly it's acting on. Right at the center of mass point, you have force of gravity downward direction, which is Fg, mg downward direction. You have a pivot point there. So because of that, there should be a normal force upward, right? If it is balanced, if there's no other, any other forces acting on the object, then if you apply sum of all the forces on y-axis direction, equal mass times acceleration on the y, then you can simply say normal force minus the mg equals 0. There's no motion. So the normal force equal mg. So the object is at balance or it is at rest. However, if you apply a force, let's say I put another mass right here. So another small m1 mass, I put like about x1 distance away from the center of mass point, right? So that's the center of mass point. So as soon as I put the small mass at point A, then what will happen to this object? This object will experience what we call the torque, right? So the torque, how you define the torque? Torque is this Greek letter, like the curly T. Torque is actually R cross F. So the torque is actually a third vector. So the torque is a result of interaction between two vectors on xy plane. So which means if I have R vector starting from the center of mass towards where the force is acting on, that is the vector R. And then I have a force of gravity on that object right here, pulling downward direction m1g. So if you take the interaction between these two vectors, if you put all your right hand, all the four fingers along the R direction, there's a couple of different ways you can do the right hand rule. All the four fingers along the first vector, which is written first on our equation, and then rotate that towards the second vector. Then you look at the thumb direction, thumb will point it out, in this case, thumb will point it out negative z-axis direction. That is negative k hat direction. So this z right here, the tau right here is actually the third vector, which is a result of the cross product between the two vectors on x and y. So this should be on negative k hat direction. Now this is generally we call the rotational version of the Newton law, right? So the linear force is F, object can move on linear direction, but object can rotate if you have a object under torque, right? So that you can identify another way. If you consider this is a screw, so let's say this is the screw, and then if you apply a force right here, this is the fixed point, okay? That is the point P, fixed point. If you apply a force exactly r distance away from this point P, downward direction, and then try to rotate the screw clockwise direction, you can see clockwise torque is actually negative. Reason, if you rotate the clockwise direction, this screw is starting to move in this direction, right? So that direction, according to our standard XYZ coordinate system, standard x-axis horizontal, standard y vertical up positive, standard z positive coming out the board, negative going into the plane of xy. So which means the clockwise rotation will always create the negative tau, we'll say generally. That negative sign means the direction of that torque, okay, where the screw is moving. On the other hand, the same condition, by keeping the same condition, if you apply a force thisward direction, let's say I'm applying a force downward direction, other side to the point P, then this is the R. When you apply the same right hand rule, you can see rotation will be thisward direction. That is generally we call counterclockwise direction, right? This clockwise and counterclockwise refers to the standard clock rotation direction and opposite to that, right? So this will rotate counterclockwise direction. As a result, that will be generally considered as a positive torque. So which means this screw is actually now coming out the plane of XY. So the screw is one way, screw is tightening up, other way is screw is loosening up. So that's the idea of torque. That's what actually we try to investigate in this experiment. It's a very simple experiment, nothing much to do. So basically, we would like to see how the application of torque can be used to understand balancing of the object by doing simple couple of calculation. Okay. Question. All right. So that's it. Then very simple idea. Now in the experiment, what we're going to do, we're going to investigate a couple of different cases. Always we're going to have one object which is going to be at midpoint, going to be fixed with the pivot point. So which means this object has freedom of rotating either clockwise or counterclockwise, depending on how the force is acting on the object. So all we need to understand is that how to measure the distance from the fixed point to the force acting point, which means always this point to the force, whatever the force acting on. Then accordingly we can, if let's say for example, if I have object here, that will create m1g downward direction. Let's say this is x1. Then this force right here will create tau, but that tau is minus. Reason is it creating clockwise rotation, right? Around this point P, it try to rotate clockwise. So that is negative tau, which is simply equal x1 times mg, m1g times the sine 90, because angle between the R and x1 and mg is 90. Sine 90 is 1. Generally, we don't write it, right? So it's going to be x1 times mg. On the other hand, that rotation I can stop if I have another object. If I find the exact location to apply, let's say I have another object m2, which applying the force downward direction m2g. Let's say this distance is x2 from the fixed point. So then this rotation is counterclockwise. As a result, that's going to be positive tau, which is equal m2g times x2. Now this one is a positive number, this one is a negative number. So if you add these two together, so I will get a 0, right? So if you add the tau plus tau minus, I should get the 0. So which means the object is at rest. So the idea is that if you have a larger object, this kind of large object, so the Newton's second law, the way you explain very beginning of the semester, we generally say that Newton's first law, whenever the sum of all the forces equals 0, that is the Newton's first law, right? So we generally call object must be at rest or maybe moving at a constant velocity, right? Constant velocity means acceleration must be 0. that law is actually valid only in linear directions. Now, after this chapter, after you finish this area, rotational version area, then you have to modify the Newton law, and then you have to add this information too. If you want to confirm object is at rest, you have to check all these conditions. You have to check all the forces on x direction should be 0. All the forces on y direction should be 0. All the forces along z direction must be 0. That's not enough. You have to check sum of all the tau at particular fixed point, that also must be 0. If all these conditions valid, then only you can confirm object is at rest. So that's all of those actually the will address along with this experiment. Okay. Any question? All right. So the experiment is very simple. So it's there's no graphing or anything, just simple calculation. You can click the simulator link on page number page number 4. PHET simulator link. When you go there, there's 3 different options. They click on the second one called the balance lab. Now you can see this is the meter ruler, this yellow color horizontal line, which I used earlier. And then the pivot point right here exactly at the center. And then this gray color 2 cylinders keep there to keep the meter ruler like that. But I can get rid of that. If you see this 2 options underneath that. Click the right hand side option, then you can see that 2 cylinders I can get rid of. Okay. Now the meter ruler is balanced. The reason the pivot point is exactly at the center of gravity point. So that situation is the exact situation which we discussed earlier, like this one, right? This one, I have the meter ruler balance exactly at the center of gravity point. There's no extra force on the right hand or left hand direction. Because of that, there's no rotation. So the meter ruler is at balance point. Now let's take a look what will happen under different conditions. Okay, that's what we're trying to do. So the case 1, so we'll try to balancing of 2 masses, right? Let's try to balance 2 masses on this meter ruler. Now you can click on forces from the object, that icon from the top right hand side, and click on the level. Then you can see that green color 2 arrows appear exactly along with the meter ruler. So I can use that green color arrows to figure out whether the meter ruler is level or not. Okay. And also you can put the ruler, click on the ruler here. Then you can see the numbers. Okay. This is not just a meter ruler. From the center, you can see each side, you can measure 2 meters. Okay. So that means the total is 4 meters long. Center point is exactly right here. You can see the numbers for both sides starting from there. Let's take a quick look. Let's use a 5 kilogram mass. You can apply the units to the mass. Force generally going to be Newton then, right? Let's apply 5 kilogram mass at about 2 meter location. Let us apply 5 kilogram mass. Doesn't matter actually, but let's take a look the position to apply the 5 kilogram mass. About 2 meter location. Yeah, let's try that. 5 kilogram mass, 2 meter location. You need to click the 5 kilogram mass and then drop on exactly on top of that particular point. Okay, if you do that, then you can see now you have a torque which is a clockwise torque now, right? Now this is creating negative torque, right? That negative sign you can get actually by doing, you can do this cross product any way you like, doesn't matter, right? Torque is equal, you know, R cross F, and the expansion is R, magnitude of the R, magnitude of the X, F, sine of angle between them, And then you have to find the unit vector n by using the right-hand rule, right? There's two different ways you can apply right-hand rule. Or you can apply this R and F in ijk vectors, right? Let's say in this case, R is 2 meters, and that is in I hat direction positive, because you measure in the R from the center towards where the force is, right? And then cross product, force is now 5 kilogram, and then force direction is negative j hat, right? So as a result, you can see, if you multiply that, and then you will get 2 times 5 is 10 kilogram meter, 2 times 5 is 10, and then R cross j, that is negative I cross j. Now this, you know, you are familiar how to do that. So the I cross j is k hat, right? But the k hat is come with the negative k hat here. So that negative sign tells you which direction this torque is actually applying. So that's the idea. So I forgot actually the G 9.81, because here I have to use, let me adjust that here. Here I have to use the force, right? So which means 5 kilogram times 9.81, then meter per second squared, which is equal 5 times 10, 10 times 9.81, which is in total you can say 98.1, right? 98.1 kilogram meter per second squared times the meter. So this part is Newton, this part is meters, and Newton meters, you know, joule, but never put the joule for the torque. The reason you cannot put the joule for the torque unless if the object is rotating, okay? Otherwise, it's not really meaningful. So we usually keep Newton meter as it is, okay? So then you have here negative I hat direction, negative I hat cross j hat, right? So that's going to be negative k hat direction. So you can get that any way you like, doesn't matter. And if you do in this way, then R is actually this word direction. That is the R direction. And then F in this case, downward direction. In this particular case, the angle we interested is actually R to F. This angle, that is actually negative, right? Because usually we measure the angle relative to positive x-axis. You go up, we generally call positive direction. You go down measuring angle, we call negative direction. So that negative sign will still give you the negative direction. Or you can use the right-hand rule. There's many different ways actually doing this calculation for the torque, okay? So you can do any way, but in this case, easiest way is actually looking into the ijk vectors. That is the most easiest way, because there's no angle between the R and F, always going to be 90 degrees. Okay, question. Then let's continue. This is a very simple calculation, right? So we have mass, which is 5 kilogram, and the force going to be equal sign mass times 9.81. And then the distance, which is now 2 meters, right? Okay. And then now, if I want to balance this object, I have to have another torque on the other side, right? Left-hand side, which should balance the clockwise torque here. So to do that, we'll bring the 10 kilogram mass, and then all you have to do just find the right location, right? If you do the math, you can find the right location, or else in this case, you can do trial and error. You can just place where you think it will be balanced. If that is the right location, it will automatically balance. If you put it very closer, it cannot balance. If you put very further, it cannot balance. Then you have more torque on your left-hand side. If you put exactly halfway, it will balance. So now the 10 kilogram creating counterclockwise torque, you can see the balance becomes green color when the meter ruler really balance, okay? Now it is white. If you wait a minute, then it will becomes green. That means it's really balanced, okay? So which means the 10 kilogram creating counterclockwise torque, which is positive, 5 kilogram create clockwise torque, which is negative. Those two should be equal to each other. That's all. Very simple idea. Question. After you figure out the location, then you can do this calculation. This you can click and drag. 10 times 9.81, and the location of 10 is actually 1 meters. Let's calculate the torque. Torque is we calculate in Newton meters, and then don't put the units joule for the torque. That actually meaningless. Okay, there's no meaning at all unless your object is rotating only. You can put joules, then actually torque dot product with the theta. Okay, so that means rotational version of the work done. I don't know whether it's covered by now. It should be covered by now. Rotational version of the work done is actually torque times the delta theta. So delta theta doesn't have the SI unit, that is radians. If you calculating that, then you can put actually unit joules. Then your object is really rotating, okay? Because to call the unit joules, you have to have the work done. To have the work done, you have to have the moving object. Otherwise, unit joule has no any meaning if you put that unit into the torque. Okay, but torque unit itself you need to joule. Okay, but we don't use joule unless object is at rest. When the object is moving, then you can put the unit joules. But in this case, because of that, we never going to put the unit joule here because object is at rest always. Okay, there's no rotation at all. Then you just calculate this. Any question? Equal sign. I need to count the counterclockwise torque. Now you know counterclockwise torque coming from the left side to the pivot point, right? So this is equal sign. I need the force on object number 2 left side multiplied by distance from the pivot point for that object. That's going to be positive number, right? And the clockwise torque, Newton meters unit again. We know that direction is negative. We can actually put here the direction of these. Otherwise, we can't put the direction directly into these calculated values. We'll put the direction into right here. Okay. Let's say this direction is counterclockwise, which means positive. Counterclockwise means technically positive Z direction. Okay. Positive Z direction. And the clockwise means you can just, that CW and CCW means the short term for the clockwise and counterclockwise. CW means negative Z direction. Okay. Then adding those two should be 0, right? Let's take a look at equal sign. Right hand side force, object number 1, force of gravity multiplied by 2. Then I should get exactly the same number here, right? Otherwise, object cannot be at rest. So that's the idea, very simple. Adding these two should give you 0 because this is on negative direction. Okay, remember, these are vectors. Okay, I'm not putting negative sign here. Negative sign here, I'm not putting there, but I'm calling it to the vector. Okay, I'm calculating here only magnitude. Okay, there's no meaning even doing the percentage error. You can see it exactly the same number. So you can just put 0 there. I just leave it there. Generally, if we're doing this in class, we calculate in the percentage error. Generally, we're going to get little bit percent error in class because distances are slightly off than what it's supposed to be. But in the simulator, you're not going to see that at all. Okay, any question? Let's take a screenshot and then let's add that screenshot into here, balancing of two masses on the simulator. Okay. And let's crop that out, anything unnecessary. maybe we don't need to show any other information than this part, right? So let's crop that out. Everything else okay. All right. Any question? Then let's continue to part B. Let's take a look how about if I have a three masses, right? So what will happen? Three masses. So if I have a three masses, case 2, I have 5 kilogram, and then I have 15. I have 10 kilogram, and then 15 kilogram, and then let's try to balance it with another mass on the other side. Though I can use 5 kilogram and then 10 kilogram and then balance with the another mass. Okay, in this case, 10 should be at 0.75 location. 15 should be at 1 meter location, other side, left-hand side. Let's bring the 5 kilogram mass. Let's try to balance the object, okay? This should be force, which is 10 times 9.81. And then the force for object number 2 equal sign 15 times 9.81. And again, the units mass should be unit of kilogram, right? Force should be unit of Newton. Pivot point, we measuring distance from the pivot point, unit meters. 10 kilogram object is at 0.75 location. 15 kilogram object is at 1 meter location. Let's try to balance this by using third object, right? So let's arrange first. You can, if you want to get rid of any mass, just click that, drag it all the way to here, then it will disappear, okay? 10 is on my right-hand side, 15 is on left-hand side, right? Let's put the 10 here. You can see it have a lot of rotational torque clockwise. That's why object rotate. Now let's bring the 15. 10 is on 0.75 right here. 15 is on 1 meters, 1.0 meters. Now you can see it's a lot of torque towards the counterclockwise. If the counterclockwise torque is larger than the clockwise torque, object is still rotating, right? So now I would like to find where should I put the another mass, right? Obviously you can see I should put the third mass somewhere on your right hand side, because if you put a mass here, then you can create another torque, or you can increase the torque towards the clockwise direction. When the two torques are equal, object will balance, right? So let's bring the 5, and then you can find the place. You can do the math with the equation to find the place, or you can do the trial and error, right? You can bring this. If I put closer here, nothing much. If I put very further here, then it too much. Rotation towards the clockwise, right? So it should be in between, right? You can slowly move this one little bit closer. Then you can find the exact location where it need to be. If it is at exact location with the right amount of torque, then you can see object will be leveled. Question? Now I have 5 kilogram object, third object. Force you can just click and drag, go just multiply, just simple calculation. And the distance you have to find, new distance is 1.5 meter location. Now let's do the calculation again, which we done earlier, right? So now the object is balanced on this pivot point in the middle. So the net torque should be 0, right? So that means the right hand torque and the left hand torque should be equal and opposite, right? So let's do the calculation. If I do magnitude only, I should get the same number. You know the clockwise is negative direction, okay? Let's do again this one. This is in unit Newton meter. And the direction also, it's better to add here. Counterclockwise torque is positive z direction, right? And the clockwise torque, unit in Newton meters, direction wise, it should be negative z direction. PE of torque, I don't know whether we gonna get any different. Most of the time we will not get it in different. If we don't, that's totally fine. There's a small typo here in the unit, in the word torque. This should be O, right? Let's do the calculation again now. Equal sign. Counterclockwise torque. In the counterclockwise direction, you have two forces, right? I have to do R1 F1 plus R2 F2, right? Cross product, but you know sine 90 in both cases. Because of that, I can do the calculation easily. So I have R1 times F1, force 1, close bracket, plus another bracket R2, not that. That should be object number 3, right? R2 times F3. Hit enter. Let's check that with object number 2 on our right hand side torque. R1 times R2 times F2, force 2. So we're getting the exact same number on both sides, right? So object is at rest. So that's what we observe. Question?
Professor, I had a quick question. I
Yeah.
just looked at it and I just thought maybe object one and object three, since they're on the right-hand side, isn't that the clockwise direction and not the counterclock direction?
Yeah, you're right. Yeah, these two actually should go here. Yes, correct. So let's rearrange this one a little bit. Equal sign, force number 2 multiplied by R2. Yep. Okay, any question? There's no meaning doing the percentage error, right? It's still 0. Okay, so let's take a picture of that one too, right? Print a screen. After you balance it, okay, it should be look like this exactly. You can see the force, locations, and the mass and everything nicely. Then let's add that into here, insert pictures, and let's put the new screenshot right here. Only this part, okay? Otherwise, that's going to be a very large picture. We don't need the other area. Only we need actually this. This is now similar to the free body diagram, right? Remember earlier I mentioned a few times the free body diagram is elongated, right, along x-axis, because you have to show exact location of force applying. If you draw the free body diagram like you usually do for the other equation in Newton mechanics, for this part of the chapter, it's not meaningful at all. You have to really show where's the exact location, because whenever we're talking about the torque, rotational version of the force, we're really interested to see that R, how far away the R apply, R is from the rotational point, the fixed axis. If that is not there, R is 0, then it's not meaningful at all because there's no torque, right? So that's the idea. So these forces should be clearly visible with the proper R. Okay, any question? All right, then let's take a look. Part 3. Let's balance two people. Okay. To do that, you have this right-hand side. You see, you can actually reset this if you click this yellow button, right-hand side very lower. Everything disappears, and then you can click again here to get rid of that cylinders. And then in the middle part right here says bricks, and then there's an arrow, right toward direction. If you click that arrow, you can see it changes into people. Then I can bring two people, and then we can balance two people, right? So I can balance one, I can put one person on 0.5 location, another person on other side 0.5 location. Let's do that. what person is here, 20 kilogram and 60 kilogram, right? So I need to find the right. Do I have a 20 and 60? I have a 20 kilogram person here. 0.5 location. Other person should be 60 kilogram right here. 0.5 location. Okay. Since the both persons are in the same location, the heavier person is on the right hand side, then you have actually clockwise rotation too much in there, right? So because of that, now the meter ruler is actually not balanced. So you have to find how much force is needed to balance this meter ruler, right? And then we can find what is the force needed to balance the meter ruler. All of them we can find very easily, right? Now let's draw a free body diagram for that one. So in terms of free body diagram, what we have now, this is the balance point. I have one force right here. Let's say this is F1. And then this is X1. I have another force right here, F2. This is X2. And then now F1 is about 60 times 9.81. F2 is about 20 times 9.81. And then I can use the torque equation to find what should be the difference between them. That should be the third vector I need, right? So I can find, actually, I can calculate how much force is needed. But in your lab manual, it actually tells you you need about 196 another force to apply for this one, right? To balance this one. Let's calculate that one. So now what we can say, the net torque net is actually torque right plus torque left. If you do that, torque right is equal x1 times F1, which is negative direction, plus torque left is equal F2 times X2. X1 and X2 is same, cancels out. Technically, this is the difference between these two forces, right? So the minus F1 is equal 60 times 9.81 plus F2 is equal 20 times 9.81. If you take the difference, then you will get the force needed, right? So you can just simply calculate that, which means 60 minus, this is going to be negative 40 times 9.81, right? So if you take a look what is 40 times 9.81, then you have the answer. Now, that is not what really interesting, because that is the force, right? I can't really apply a force here. I need to apply some sort of mass to create the force, right? We can find the amount of mass needed easily. How to do that? So I have, what is the number? 40 times 9.81, about 392.4. So if I divide that by 9.81, then I can find the amount of force needed, the amount of mass needed exactly. Question. Okay, so that's where you can do the calculation, but the calculation is not really important here, right? We can actually do that another way, like the question is asking here. Question is telling you the only way to balance the system is by adding the 196 force that when applied to the system, it will cause the counterclockwise torque. Use the torque equation to determine the point where the 196 force should be applied. So can you find that where the 196 force should be applied? So what we should do? To have the torque net here. Torque net is actually force times the displacement, right? So I can argue that this is equal minus, if you multiply these two together, you will get about like 392, 40 times 9.81. That is about 392.4. then I can argue that this should be equal now some third force F3 times the R3. Now all we have to do, force F3 times the R3 is actually equal 392.4. Force F3 equation is telling 196, right? So then I can easily find the R3, 196 times R3, which is equal 392.4. So the R3 I can find roughly about 392 divided by 196. So then you can find the answer where that force is supposed to apply, right? 392 divided by 196. So you should get about 392 divided by 196. We're getting about like 2 meter location. So I have to apply that force exactly around close to 2 meter location. But that should create counterclockwise torque, right? So that means I should apply a force somewhere here, somewhere exactly this location. Now, if you want to figure out how much weight is need to be applied, that also I can do because I applying about 196 of force, right? Force 3 should be about 196 of Newton. Then I can divide that by mass 3 needed is force 3 divide by the gravity. So if you divide 196 by 9.81, then you will get about the mass is needed. Then you will get a number about like 19.97. That is close to about 20 kilogram, right? So technically you can recalculate, estimate by doing that simple calculation, what is the weight needed to apply on left-hand side. Then let's check this. If our calculation correct, if I bring the 20 kilogram and then place here, oops, it's not balancing out. Why is that? Let's see. Where did I did any mistake with the calculation? Oh, let's see. That's fine. So we can find easily the answer where it's supposed to be by actually moving it. Okay. I think I did somewhere a simple mistake. So the balancing exactly at, you can click the leveling too. Balancing exactly when you put the 20 kilogram at 1 meter location. Okay. You need to do this calculation again to check that. Okay. But that's the way you have to calculate manually. So that will be useful for your exam anyway. With this area, you need to do such a calculation. Take a look at that again. Okay, I probably did some mistake somewhere here. So I got 2 meter after I did the calculation, but technically it should be 1 meters. Okay. Question. Okay, so in the experiment, we're not trying to do that whole calculation manually, right? So we can do it experimentally. All I need actually to identify how much weight is needed and then bring that, and then I can do just the trial and error to figure out where it's supposed to go. So that way I can easily figure out experimentally, but in the theory class, you may need to do that calculation correctly, okay? Any question? Okay, mass in kilogram, force in unit newtons. Do that calculation yourself. That will be useful, but I'm not going to do it again. Okay. Distance from the pivot point, unit meters. Person 1, let's consider person 1 is 20 kilogram guy, small guy, right? And multiply by 9.81. Have the weight. And then the distance from the pivot point is about 0.5. And the larger person, 60 kilogram person. And the weight apply on the larger person is about 588. Distance is same 0.5. Counterclockwise torque, Newton meters. Clockwise torque, Newton meters. Torque needed to balance the object. So we can find it easily. Torque needed to balance the object is actually difference between these two torques, right? So that is again Newton meters. Counterclockwise torque coming from the left-hand side, right? Left-hand side is the smaller guy. So that is person 1 multiplied by the distance. And then the other side, clockwise torque equals sine person 2 multiplied by the distance. So that's where I think I probably did the mistake earlier. That number was 300 something when I did there. Okay, question. And the torque needed to balance is actually different between them, right? 296 minus 98, 196. And torque needed to balance the object is 196. Now to figure out where it should be applied, I have to first figure out the mass which is needed for this one, right? So the mass needed for 196 is actually, you can find, I don't have a particular space there, but you can write here. Let's say mass needed for this one, M, it is 196 divided by 9.81. So let's say mass 3, which is roughly about 20 kilogram. Then if you have a 20 kilogram, then you need to figure out where it should apply. So theoretically, I can do the theoretically in my equation, or experimentally, I can bring the object, amount of mass, and then take a look where it's supposed to be applied. Then experimentally, you already figure out position to be applied to balance the system is about 1 meter location. Now you can recheck this again. If all correct, then if you rewrite this equation, then you should get the 0, right? So the net torque acting on the object now must be 0. So which means I have negative torque coming from the larger person, right? Your right-hand side, clockwise torque, that should be 60 times 9.81 times 0.5. And then you have positive torque coming from 20 times 0.5 times 9.81 plus another positive torque coming from the object 20 kilogram times 9.81 times 1. If you add all of these together, you should get 0. You can check that. If not, then what we observing should be incorrect, right? Since we observing it correctly, this must be 0. Any question? Okay, so that's the idea. I think you get the idea, right? Any question? All right, then, I mean, that's it. This calculation you can check again, okay? That will be good practice anyway. Let's take a look then last part. So what is asking in the last part? Oh, we need the screenshot, right? After you properly balance it, let's take the screenshot. And let's add the screenshot into here, part 3. Let's add the screenshot to part 3. Right here, okay. That should show it is properly balanced, okay. This arrow should be green color. All right, so that is our part 3. Then let's take a look, couple of other scenarios. So there's the couple of objects you can find called the mystery objects. You can reset this again, click on the level and the meter ruler. And then in the bricks right here, if you click the right arrow all the way to the end, you will find the mystery objects, right? Let's try to find the mass of the mystery object by using the method of torque, right? So the idea is very simple again, the torque equation, right? You have a meter ruler and then it balance here. You bring the mystery object, let's say I place it right here, x1 distance, this is object A. And then if I want to find the mass of the object A, this is going to be ma times the g, right? x1 I know, this will create the torque negative direction. I need to bring the known mass and then put in this side. Let's say I have m of 0 known mass. This will create m0g, and then this is x2. Then you can use the torque method to figure out what is this mass say, right? We know if it is a balance, net torque should be 0. So I have negative mag times x1, positive m0g times x2. Then from there, I can easily find ma, which is equal, g cancels out, m0x2 divided by x1. Right? So that's the idea. So the x1, x2 we can measure directly. m0 is a known mass. Then I can figure out unknown mass very easily, right? So we can find all of these unknown masses, A, B, C, D, by just simply doing this technique. That's the last part. So the distance from the pivot point, again, unit meters, mass of the balancing object, kilogram, distance from the pivot point, unit of meters. So we need to calculate the mass of the mystery object in terms of unit kilogram. Now you know the method to calculate. Let's start from the object number A. Let's take a look where the good position to keep it. Doesn't matter. I think we can place anywhere and then try the other side, trial and error method. Okay. So yeah, let's do that way. So let's bring it and then place it like 1 meter location. Get rid of the cylinders. You can see it creating the downward torque, clockwise motion. Now I need to stop that motion, which means you have to go back to the bricks. And then this object seems to be not very heavy, but we can try with the little bit heavier mass to see where I can place it to balance. If I place it too much rotation, if I place into 0.25, if I place into 0.25, not good at all, then you can slowly bring it other side to see where it's going to be balancing this object. When it reached the 20 kilogram at exactly 1 meter location, it balanced. Now, this calculation is very simply, you can say even without doing any calculation, object A mass should be 20 kilogram, right? Because both are in the same places. So the torque from the counterclockwise should be equal to the clockwise, right? Make sense, question? Object I place on 1 meter location. Balancing object I use 20 kilograms. Distance for the non-object 1 meters. So if you use the torque equation, equal sign, mass M2 multiply by the R2 divide by R1. So that's going to be 20 kilogram, okay? And then you can take the screenshot. That is screenshot we can add here. We'll add all 4 screenshot, okay? Any question? All right, then let's go. It's the same thing technically. There's nothing new to do, but we will try that with the other few objects. There's 3 other unknown objects, okay? Let me copy paste that equation in a bit, okay? Let me crop this one. Because I wrote that equation there, that will be useful actually for next part. We can use probably directly. Okay, that goes here. So that's the equation we are using there, okay? Let's say this is the mass of the mystery object, right? Okay, so then all we have to do now, let's try the other, there's a couple of other mystery objects, right? If you go back again to that place, you can see 4, right? Let's try other ones too. Let's get rid of A. Now we know that mass. Let's do B. Let's bring the B and then place on the same location. Now you can see it's too, look like not enough torque, right? So the 20 kilogram is much heavier there. Let's move it closer, much closer, much closer. Okay, right there. Then it will be balanced. Okay. Then we can find it out that you know now the distance of the mystery object. Mystery object distance. I'm still keeping the 1 meter. Doesn't matter technically. You can place this any place you like and then just rearrange the 20 kilogram until it balance, right? This is experimentally we try to find, not the calculation way, right? So the earlier we discussed, you can actually calculate everything, but that is for your lecture class, right? Here we interested more experimentally how we determine this. And that's it. It's very simple. Then I know I'm still using 20 kilogram object, non-object. Distance of 20 kilogram now at 0.25 meter location, right? Since I used the equation earlier, that's why we use the equation. You can just click and drag now. It will give you, now you can see object number B is actually much lighter. So that's why you have to bring this heavier 20 kilogram much closer, right? You see earlier, both are at the 1 meter location, right? But now it's different. And then likewise, we can figure out all the other objects. Let's get rid of this one. Let's try the objects. Oh, before you getting rid of, you have to get a picture. Okay, guys, any question? Take a screenshot because we need that picture, all 4 pictures. We'll add into here. Any question? Okay, let's add this picture into here. And only 2 more objects to go, then we're done. Okay, it's a very simple experiment. All right, so that is right here, case B, and then let's do case C. To do that, we'll get rid of object B, we'll bring the object C, we'll place back again at 1 meter location. Now you can see 20 kilogram is not enough, but however, I can get the enough torque by increasing the radius, right? Let's bring it away from there. That seems to be too much. Let's bring it a little bit closer, about 0.75. Yeah, that works nicely. So you can just calculate now the distance from the pivot point. Object C is on 1 meter location. Mass we still using 20 kilogram object. Distance now at 0.75. If you calculate with the same function, then you will get the object number C actually about 15 kilogram. Okay. Take a screenshot. That should go here. Anybody have any question? Okay, then let's take the last one, last object. That is unknown object number D. So get rid of C, bring the D. Let's put back again at 0.1 meter location. Seems to be not enough torque. If I move into 0.5 location, it can balance exactly. Take a screenshot. Let's do the calculation. 1 meter, 20 kilogram is still I'm using. Now this is at 0.5 location. If you do the torque equation, then you will get that is about half the object, non-object 20 kilogram. So let's add that picture into here. So that's it. Any question? Okay, so I think technically that's it. We done all of them. So that calculation you can check later. And we can officially stop here. If you have any question, stay on the call, okay? I will see you guys then next week.
Professor, can you click back onto your simulator for a second? Thank you.
Hello, Professor. Hello.
Anybody have any question?
Yes, Professor.
What's up?
I still have some outstanding labs here that are trying to submit within this coming week. I just wanted that'll be okay. The lab reports.
Oh yeah, that's fine. But the upload everything into the Blackboard. Okay, still those links are open.
Okay, thanks a lot.
Yeah, no problem. Yeah.
Hello.
Yeah, what's
Professor?
up? Yeah.
Can you go back to part 2?
Table 2.
Yes.
Mhm.
I'm sorry. Give me one moment. My computer just kind of died. Can you go back to the oh my God, this is being so much of a yes,
Yeah,
the
what's up?
balance, the counterclockwise and the balancings.
Okay. This one.
Yes. Sorry, just give me one moment. My computer just got
Let me
stuck.
go back there again. This one. What is the question then?
Oh, I just need the formulas for both.
Oh, how to
Yes.
calculate that? Okay, that's going to be, this is counterclockwise. So counterclockwise come from the left side, right? So the left side, it was object number
The
2. Object number 2. So that should be D25 times E25. D25 times E25. These two, okay. When I click here, you see the formula here, right? You see that?
Yes, I've seen it. D25. Okay, and the second one should be the one with the parentheses.
Second one should be adding both of them together, because in that particular case, there was 2 objects on the other side. Let me expand this one right here. You see there's 2 objects on the clockwise side, right? So I have to do both of them 10 times 0.75, 5 times 1.5.
Okay, so it will be D24 times E24 plus
E24 times D24 plus then E26 times D26.
makes perfect sense. All right, thank you so much.
Yeah, no problem.